I put it in the chat box. Today's topic is Rust versus C. It's going to be a very basic introduction, but also more importantly talk about the pros and cons of C, mostly the cons of C, and how Rust can actually solve some of those cons, or rather, how does it actually solve those cons, and why it has the potential to actually replace something like C, which is already pretty much underway. I'll talk about some of the examples as to how there's a lot of momentum in the transition from C to Rust. All right, now heads up, the first point I'd like to make is this material that's going to be presented is fully open source. It's by a person called Kevin Booz. He owns a project, an open source project called TCS OS. He's building his own operating system. He's actually a professor. So these are his slides, and I've taken his permission to sort of use them as is, maybe sort of add a couple of things here and there, but they're his slides. All right. So with that out of the way, let's talk about the agenda for today. Before I go forward, Uday, I hope you've already started recording.
Yeah, I started.
Okay. All right. So the basic idea is we look at what's good about C, what's bad, and also some really gnarly things that keep coming out of C. When you sort of come across these bugs, you'll feel like, okay, is it that simple to shoot yourself in the foot? Is a question that will pop up. We'll talk about those kind of bugs. Then a bulk of the time we might spend it in introduction to Rust, not the syntax, but the features of Rust, predominantly things like ownership and borrowing, and how those things actually help against some of C's problems. All right, and then we can open it up for Q&A and any questions you might have. All right, so let's get started. So what's so bad about C, and sort of what needs to change? What you would rather not have that you already have in C. But before that, let's actually talk about what's good about C, right? The thing about C is that it's a very straightforward, easy programming language. It sort of tries to stick very close to the machine. It produces efficient code. There's no layers of abstraction. Even in C++, you have a lot of different things that can keep happening. But in C, what you see is what you get, kind of a scenario. And that's very important when it comes to resource constrained environments. Something like your, low power, sorry, not just low power, but your microcontrollers, your constrained devices, all those kind of things. This becomes very, very, very useful. And the other thing is you also get direct control over hardware. We'll talk more about this, but you don't have to go through, when you actually want to talk to hardware, you're not going to go through multiple, you can say, multiple layers till you get to the hardware. So that's another thing. And then the important thing about C is that it prioritizes performance. All memory management in C is manual. That is allocation of your, allocation for some memory on the heap, managing its lifetimes, all of those things are completely manual. There's no such thing as a garbage collector in C. And this is what usually professional developers, people who spend years in the industry, sort of gravitate towards, because it offers all of these things. So that's the good stuff about C. Now, when you get all these good things, you also come with, a lot of the other things that, because you have so much control, you have so much at your fingertips, what can go wrong? So firstly, let's look at what C's type system. C's type system is, it's not strongly type. It's a weak type system, in the sense that it's easy for a developer or programmer to take an integer in C and cast it. In other words, basically transform or convert it to other types on the fly. And C is happily going to allow you to do that. It's not actually going to stop you. The C compiler will not stop you from doing that. You can cast from unsigned to signed, and as you'll see some of the examples I have, you'll see that what could go wrong over there. And then overflow, underflow. Overflow is this thing called the wraparound effect, where let's say you have a 32-bit unsigned integer or a signed integer. A 32-bit signed integer is actually, it has a, it sort of has a maximum and a minimum value, and beyond that you keep wrapping around, and that wraparound effect actually fails silently in C. Also, the important thing is type interpretation. For example, if I've already declared, say something like int x equals 5, which means it's an integer, I could also go ahead and convert, or rather reinterpret the same type, the bits of that value, as another type, and that's allowed in C. It's what you'd call transmutation, but that's allowed in C. Now, with all of this said, because when you actually use types in C, they're not actually strongly typed. They're not. The compiler is not going to stop you from, whenever you come across errors of any of this kind, any of these errors, the compiler is not actually going to stop you. You're okay to do this in C. In C, the other thing, apart from the weak type system, is memory mistakes that you get to make. You can have things like null pointers. That means your point. So firstly, everything in C is, when you're dealing with, you'll be dealing with pointers a lot, and things like null pointer dereferences, no bounds checking. That means, let's say you've allocated some memory that's the first 6 bytes on the heap, and then your code is, you're writing code in such a manner that you're not going to access the one of those 6 bytes, but you're going to access the 7th byte. That's an out of bounds access actually, but that's allowed in C. Similarly, things like string formatting errors, null terminated strings, etc. These are the simple ones. Then there's more complex stuff like dynamic memory leaks, in the sense that you've allocated memory, but you forgot to free it. Now it's already taken out space from your available amount of memory that you have. So that's a memory leak. Then there's things like use after free. You've allocated something, you've allocated memory on the heap, and you've freed it, but you're again trying to use that, whatever is in that same location. That's a use after free. Then a double free, will get to it. But all of this the results have been catastrophic in many scenarios. Crashes, severe security vulnerabilities, lots of, you might have heard of these things called CVEs that keep popping up. TLS will have a bunch of them. The operating systems will have a bunch of them. The browsers will have a bunch of them. You name it. Any application that's probably written in C or other memory unsafe languages, this is one of the biggest problems that you see. This is what we call memory unsafety. So the reason for this is very simple, because it is up to the programmer. It is on the programmer to check all of this, to make sure that all of this is not happening. And that's what we mean by manual memory management. That is something that C has to do. Right? Now, do developers, really make such mistakes? Is C actually to blame? Well, the question is, it's actually a bit of both, because C provides all of these opportunities for you to make those mistakes. And it's easy for us to say that, the developers should be really good, etc. But given the volume of code that we write, given all of the things that we sort of have to deal with when in software development, it's not actually a valid ask to put this kind of responsibility on the programmer. For example, even expert developers have made such mistakes. So there's a bug that I'll be talking about, which is FreeBSD is an alternative to something like the Linux kernel. It's a Unix-like distribution. So there's a particular function in there or particular API in there called getPeerName, which effectively calls something called copy from kernel. All right. Copy from kernel is basically a function that takes that takes a buffer, a user supplied buffer of memory, and the maximum value for that, how many bytes you can sort of put in that, how many bytes is that buffer, and then you simply copy whatever is in the kernel into that buffer. That's the basic idea of copy from kernel. Now, what happened over here was, this is a very, very simple bug. If you actually see, if an adversary was to go ahead and do something like this, let's say this is the memory that's been allocated, this is a pointer to the memory that's allocated, and this is the maximum length of that buffer. Just assume that is the case. The thing about here is memcopy is actually this particular argument that memcopy takes, it's an unsigned integer, whereas copy from kernel takes a signed integer. That's the only difference. Now, because of that, what happens is if there is an adversary who passes -1 into the max length field, there's a bunch of checks that happen. The developer is an expert developer. They're actually working on the FreeBSD thing. So when they actually sort of pass -1 in there, you'd see that it actually evaluates to false. And so we end up choosing the maximum length of the memory. That means the entire kernel memory in this case could be copied out, which is this large number, because -1, if it's unsigned, when you actually interpret it, the bits, you actually get this value, right? So that would lead to being able to access the entire kernel memory, right? Now that's a bug that, was a pretty serious bug when it was discovered, and it was fixed as well. But that's the simplest thing over here. Was there's a type mismatch. There's a type mismatch between what is expected in memcopy versus what I get from copy from kernel. Right now in Rust, this would just be a type mismatch. It wouldn't work. The compiler would block it. You can't compile this code, in other words. So the good stuff about C is that it's lightweight. That means you have low-level control over memory. That also means that if you actually take something like this, let's say I have a struct in C, and I go ahead and allocate some memory for that struct, and then I access. So one of the elements of this of that struct is A, and the other element is B. Just examples. Now, if you see over here, this is what it looks like on the stack. All right. So the memory representation is that I have the pointer on the stack, and the actual struct is allocated on the heap. That's what an allocation is doing. On the heap, I've allocated my struct. The stack holds the pointer to that, allocation. Now it's easy for me to access that that member of the struct, which is A, which is what this pointer A is doing. So it's very precise. It's, for example, assuming that int A and int B are each 32-bit, this will be exactly a 64-bit allocation, which means it will be a 8-byte allocation. Yes, it will be an 8-byte allocation clearly on the heap. So that's very good. And we can access the value as well, which is a pointer with the arrow mark, and you will be able to easily access the pointer. You'll also be able to set the value of it. You will also be able to free it. So that's a very lightweight reference that you have, which is the pointer that we have. that's stored on the stack. That's a very good thing, actually. But now, when you free it, it goes away. The entire allocation is freed. You now have a pointer. You can't use that, so that's good. So up to this point, we're good. We don't have a problem. Now, that's why the explicit destructor is destroying the pointer that we initially, have on the stack. Now, what can happen? That's a very simple example. If you make that a little more complex and you say, okay, instead of one pointer, what if I have two pointers to the same allocation? To the same allocation, if I have two pointers. So pointer one is, as you see, it's PTR in this case. And then we say there's an alias. An alias is nothing but, it also means that, I'm also pointing to the same thing. So in this case, I have the extra pointer, which is again pointing to the same location. Now I free the first pointer. So when I actually call free on the first pointer, what happened in the last example was we completely freed whatever's on the heap, right? Now that's what a dangling pointer is. So, but we still have the alias pointer, which was originally pointing to the same location, that still exists. When we try and access the member A of that dummy struct, that's basically a dangling pointer where we don't know what we're pointing to right now, but we still have a pointer to it. And that's a big issue. That is what we call a use after free, right? And then if we again free that, that's a double free, right? These two cases are what we call non-deterministic. Anything can happen. There can be any kind of scenario which can turn into a security vulnerability, which may crash the program, etc. Right? So that's another case. Now, well, that's good. So those are all that's just a very sort of overview of C, the good stuff and the bad stuff. Now, considering what we've seen, can we do better? Yeah, so there's a lot of examples. You might be wondering, okay, yeah, what about all these other languages like Java, Python, Ruby, C#, Scala, whatever? Yes, they're very good. They've tried to solve this entire memory management problem by doing it automatically for the programmer. So the programmer doesn't get to directly, so you as the programmer don't get to directly access or allocate memory. That's completely, behind something called the runtime memory manager, which is nothing but a garbage collector, right? There's no, for example, what I mean by no memory management for the program, I mean that you don't have to explicitly say, okay, allocate this amount of memory on the heap, deallocate this memory, etc. You don't have to do any of that. So since you, the programmer, don't have to do it, I've taken away that responsibility. So there's no memory corruption issues like the ones that we've seen in the previous examples. However, now you don't get that for free. Obviously, that there's going to be a cost for it. The cost is that you have the runtime has to keep a track of all these different references, who's allocated what, are there references still left, should I just drop memory and clean up stuff? So all of that is actually managed by the runtime. And that is why these memory managed languages, or all of the managed languages, ship with what is called a garbage collector. Now, because that is there, the way the garbage collectors usually work is they actually pause during the execution of a program. They pause the entire execution and they look around in memory to see, okay, what needs to be garbage collected and what does not need to be garbage collected. And that's not very good for things like real-time systems, basically, bare metal systems, etc. Okay, yes, everybody else can hear me as well, right? I'm sorry, I lost power at my place. Okay, so I'll guess. So everyone can hear me. Just double checking.
Yeah.
All right. So I was just saying. So Yeah, so I was just saying, that's the problem with managed programming languages is that, we have to have this thing called the garbage collector that pretty much has to do the memory management for you, which makes your code size really large. They usually ship with a lot of other stuff like VMs, etc. It requires more power, more memory, etc., which is not really amenable to something like a bare metal system, right? Or rather embedded systems. Now, for systems programming, what is an ideal programming language? What's a good programming language for systems programming? What are the requirements first? It must be fast. It must specifically have a very minimal runtime overhead. That means there should be nothing like a garbage collector, etc. And it should also support direct access to memory. That means direct control over memory as well. But we need something that's more safer than C, or rather even worse than that, which is assembly. This is sort of a this is not a strict set of requirements, but this is a good to have set of requirements when you're talking about systems programming. And the Rust programming language fits this bill. It sort of, when it actually came out originally, it actually positioned itself as a systems programming language focused on safety, speed, and concurrency. But over these last 7 years since the 1.0 release has been out, Rust has become much bigger. Of course, you can do systems programming. You can write your own operating systems. You can write bare metal firmware. You can write networking stacks. You can do all of that, which is all systems level programming. But now Rust has grown bigger. It's used by web developers, which make up a large number of developers. It's used in the scientific community. It's used in different places now. All right. So the usefulness of Rust has expanded quite a bit, because lots of industries seem to want the same thing. They want safety and performance and reliability. And that seems to be working really well for Rust. So given that, let's talk about Rust as a high-level overview. I mean, its origins, where did it come from, etc. So there's this person called Graydon Hoare. I don't know if it's Hore or Hoare, so Graydon came out with the initial sort of version of Rust, and later on Mozilla sort of took that up. The company Mozilla took it up, and in 2015 they came out with version 1.0. The primary focus was memory safety without any performance drop, which means no garbage collection, but you still get memory safety. How do we do that? That's one. Second thing was, you must have things like more advanced features like C++, but should not be as confusing as in C++. C++ has a lot of good stuff built into it, but a lot of the stuff is all opt-in. It's not by default. That means you, the programmer, have to opt into it, right? So, and then it's, at least in the author's opinion, which is Kevin's opinion, it is well equipped to replace C. It is my opinion as well. It is well equipped to replace C. There's a side note over here. Right now, apart from C and assembly, the Linux kernel is adding support for Rust. That's the only other language that's been added for kernel development, Linux kernel development in the last 40 years. So take it for what you will. And the other thing is, Rust has also been the most loved language on Stack Overflow for the last 7 years, including 2022, right? But the last point that I mentioned, when you start learning out, you will say that is absolutely not true, because Rust will give you a lot of heartache when you start learning out, because of the learning curve is a little higher. So that's something that you might face. But as you sort of cover that, as you sort of go over that learning curve, you will see the benefits of Rust. So what is so great about Rust? Firstly, Rust has this there's high-level constructs that you can talk about. You can actually do high-level programming with low-level control. That's the way I would put it. You can sort of, it feels like you'll be writing code in Python, but you're actually doing memory management at the very low levels. It has both functional and imperative code style. It is a strongly statically compiled language with type inference. I will talk more about what all these, what all of this stuff means. Immutability by default. So we'll talk about immutability as well, but basically mutability is an opt-in, not a default. And then there's also this option of what we call ownership and borrowing, which is we're going to spend a lot of time. The other thing about Rust and about ownership and borrowing is this concept called mutability XOR aliasing. You can either have one of these, you can't have both of them. And all of this stuff is going to be checked at compile time. All right, these are the features that are very, very much talked about in Rust. Now let's dive a little more into what these things actually mean. So yeah, as I said, the one thing that the cons of Rust is that there's a high cognitive cost in the sense that the learning curve is high. So because we as programmers are not used to, unless you've been working in C for a really long time, this will be like heaven. If that is not the case, if you've been working in other languages for a really long time, then this might feel really, unwieldy, unnecessary, and sort of ridiculous at some points. But once you sort of jump over that, you start to see the benefits of Rust. And mostly the pros outweigh the cons. There's also a phrase that's used in Rust quite a bit, which is called fighting the borrow checker. Fighting the borrow checker is a common phrase that you might hear. We'll talk more about what that means. But that is something that you might hear a lot. Just a quick check, Uday, is my video visible?
Yeah, it's visible. It's clear.
Okay, just check. Right. So a brief introduction to Rust. So I mentioned strong statically typed language. What does that mean? It basically means that every type, every value has a type, and that type is actually inferred or determined or defined right at compile time. Even before you compile the program, that means even before you compile it and generate a binary, the compiler, when you start compiling the code, it will check to see whether every type that you've declared, is it a good type? Is something wrong with it, etc. So for example, if I say let x equals 5 and I actually annotate, so this is called annotation, type annotation. I'm saying that x is 5, but x is a 32-bit unsigned integer. And I'm clearly calling that out. In cases where I don't call it out, the compiler will infer it. We'll assume, okay, you're saying this is 5, right? Because you've not given an explicit type, so I'm going to assume that this is a I32. Depending on the system I'm in, it's an I32. But at some point, if I decide to use that type and I say, it's an I64. That, for example, I pass this x to a function, but that function only takes an I64 argument. Then automatically it will infer that, okay, x is an I64, not an I32, because the function definition to which you're passing it says that the argument is an I64. So that's type inference. And then you can also call out the type, in this manner. This and this are pretty much the same. Here you're saying it's a float. Here you're saying it's an integer. And then you can also have this other thing called platform dependent unsigned integer, which basically means that I don't know which platform I'm going to be running on. I might be running on 64 bits or 32 bits or 16-bit or depending on what. So you just use a use size or an I size, and the compiler will automatically, when it compiles, depending on the target architecture, it'll figure it out. You don't have to worry about it. The same thing over here. So this in Rust, there are two types of strings. One is your heap allocated string, which means you actually allocate the string, which is in this case hello on the heap. That's why it's called a heap allocated string. The second case, hello, is actually what you call a string slice. We'll talk more about that. But those are the two types of strings. And then you also have things like Unicode character representation, and in C, the C style character, which is a single byte character, in Rust is specifically called out. You're specifically calling it a U8, which is a single byte, 8-bit. So by the way, this 32 means 32 bits, 8 means 8-bit, F32 is again 32-bit float. So the idea is numeric types have specific width, and when you actually have specific width, the compiler, you will not be able to go ahead and promote, coerce any of these numeric primitives to create bugs, right? So that's a very good thing. That's a strong typing part of it. And static part of it is all of this is being checked at compile time. Okay. So the other thing about strong static typing is for something like Boolean values. In C, you can always have, you can either have a 0 or a 1. This numeric value seems to keep it is sort of ambiguous depending on how you're doing the implementation. In Rust, there's a very specific bool type. It's not a 0 or a 1 actually. It's true or false. Unlike C, where you sort of use the 0 or 1, which means you're overloading the meaning of 0 or 1 to mean true or false. And that can lead to varying interpretations in different API calls. Then one of the best ways to sort of explain this is something like PHP. String compare was a function that returns 0, and that could mean equality and failure at the same time. 0 could mean both things at the same time. Now that's a big problem, right? We don't want to do that. I think we should just avoid doing something like that. And that's something else in Rust as well. Here's an example I was talking about, underflow and overflow, where that the unsigned integer and signed integer. For example, a signed integer will assume that these are the values that the unsigned integer will have in a typical system. So in C, when I say that I can actually do this, I can say that this is an unsigned integer, A, which has this large value. B is a signed integer, which is -1. I can actually equate both of them. I can say, if this and this is equal, then go ahead and print this. And this will actually work in C, because C will happily go, the compiler will happily go ahead and say, yeah, let me just reinterpret, let me just look at the bits. Yeah, it makes sense. That's what the value is, because -1 is represented as this value, right? So it'll work. In Rust, that's a straight out error. So if you do the same thing, that is, you put this value and I'm calling this -1. You see, I'm annotating the type over here. You don't have to, but if I'm just for argument's sake, we've annotated it over here. When we sort of equate them, we can't. So the program doesn't compile at all, right? That's pretty much preventing what we call overflow or underflow or issues with that kind of case. This is where you're actually trying to cast and promote one type, which is an unsigned integer type, to a signed integer type, or the other way around, right? Those sort of things are not possible. The other thing about Rust is casting. Now, okay, so how would you do that in Rust is the question. Like this example, how would you do that in Rust? Well, let's take this example where you see that the character, or rather C, is a variable that takes the value 128, and then we are basically casting it to an unsigned integer, and then we just print it out. We print UC out. Now we get some random value, right? The ideal value was 128. When we sort of cast it, our intention may not have been this. In Rust, here's what happens. You're actually going to see this particular warning. That means it's not silently going to just go ahead and cast. If you really want to convert, say an I32 or an I8 to a U32, you can do that. Nothing's stopping you, but you're clearly going to call it out, right? You're clearly going to call it out. And when you clearly call it out, you get warnings as well to say, do you really want to do this? Because this is what you are asking me to do. The compiler will tell us that, right? So when you're doing promotion or casting from one primitive type to another, you get these kind of benefits in Rust with these kinds of warnings. Then look at Rust versus C typing errors. So this is what we call the wraparound or the underflow overflow scenario. Here you see that A is equal to 4. I start out as an unsigned integer. Then I say, let's just subtract 3 from it. Fine. Then again, I print it, while I print it, I subtract 2 from it. Then I get this really large rubbish number. That's obviously not what I was looking for. What I was looking for was something like this, where I have 4 over here and I'm subtracting 4 minus 3 is 1. If I do a 1 minus 2, it should just panic. By the way, this is in Rust is not happening at compile time. This is happening at runtime, but you're getting it at runtime. It actually does the check for you, right? So this is Rust versus C typing errors. Now, if you look at something like arrays, when you talk about storing, data in a sequential manner in something like an array. So basically, contiguous bytes are stored one after the other in memory. That's what an array is. Here's what it looks like in Rust on the right-hand side, where you see that. And here's what it looks like in C. So if I was to compile this in C, you see that I have about 8 elements over here, which is what 8 is, but I'm doing a check for less than 10, which is I'm going beyond the number of elements that I have in my array, right? And here I'm doing the same thing. So what happens when you actually run this is C will happily go through, no problem. But Rust will panic because it says, okay, I don't think this is going to work because you only have 8 elements, right? So that's the other, this is another way that Rust actually says, because it's strongly typed, because of using that strongly typedness, we can actually write the implementation to say that go ahead, panic on this, check on this and panic. I'll show you another way where we'll talk about later on, where this particular implementation of Rust is a little inefficient because we are doing this at runtime. This check is happening at runtime. There is a performance cost for any runtime check. In Rust, you don't actually have to do it this way. But this is just to let you know that, here's what happens when you compare it with C. OK, I might be going too fast. Just to take us a pause. Any questions so far?
No. Yeah, I think the last example right there, I think even the C will throw error telling that index out of bound here because X will become 9 and sorry, I will become 9. So nums of 9, I think it is not available.
So C will not have a problem accessing that 9th element.
Yeah.
Right. So C will not have a problem accessing that 9th element. That's the whole point. So if you go back to the, let me just go back all the way. So when you come here, this is essentially what's going to happen over there. When you try and access the out of bounds element, C will allow you to do it. Maybe, oh wait, not this. Oh, I didn't include that. Anyway, so I'm just going to go forward, but I'll just sort of explain that to you. So in this case, this particular C implementation, you will see that it actually will go ahead and say, fine, you're asking me to check this element after here. I'm going to check the next byte, right? assuming that these values are all 8-bit integers, because even the typing is not very clear over here. It's very clear over here, right?
Yeah.
So you're asking me to check that. Okay, I'm going to go ahead and check that. Whatever the value is, I'll go ahead and print it out. Let's see. If it's a rubbish value, then I may end up crashing the program, right?
Okay. Okay, yeah.
As far as I understand, even C does not check this. Nihal was right in this point. But if we run the static check, definitely the static check should be able to detect it.
Yeah.
But it is on top of C.
Yeah. So if you apply, the static analyzers and, code checkers and all of that stuff, though that's the investment that you make. In order to get what Rust is giving you, you apply those on top. So by default, and plus you have a number of different compilers. That's also another thing that we can talk about. Those are the other permutations and combinations. So Rust and bounds checking. Now, again, here, if you look at this is a vector. So by the way you allocate a vector in Rust, that a vector is nothing but something that you put, it's a growable array. It's a dynamically growable array, all right? When you allocate that on the heap, when you put a vector on the heap, you normally use this. This is called a macro, which I'm pretty sure in C there are macros which we can use, but in Rust, honestly, I don't like macros either in C or Rust, but it's something that we have to use because of various requirements and reasons. But anyway, the vector is allocated on the heap, all right? And then what we're doing is we're basically going to use this very Pythonic style for x in 10 elements. Go ahead and just print it out, right? We're just going to do this. Now, when we actually do this, as I mentioned, will go through. You're actually trying to print out the elements in this particular range. You're trying to work on it. You're basically checking bounds on every axis, and this will error out because you don't have 10 elements first thing. You only have actually 7 elements. You don't even have the 0. So this is going to error out, but you can actually access these, as I mentioned, instead of using this normal for loop, which uses this 0 to 10 mixture, you can use what is called an iterator. An iterator is a concept that you may have come across in things like Python and other languages. That's a high-level feature now brought down to a systems programming language where you can do the same thing. This is more efficient, whereas this is not doing, we are actually doing the runtime checking in this implementation. That means we compile the code. The code is now a binary. When it's running, we are actually going and checking, are we out of bound? Are we out of bound? Are we out of bound on each axis? Here, that's not the case, where what's happening is because we know that we've converted something into an iterator, we know its size. At compile time itself, we'll just say no. Right? So that's a more efficient way of writing code in Rust. And you get the same performance, by the way. Right. The other thing that I will say over here is you might hear something called zero cost abstractions in Rust. Like a lot, you might hear that. Zero cost abstractions in the sense it basically means that you don't pay for what you don't use. So if I build an abstraction in such a way that whether I use it or not, I'm paying for it, that's a problem. Right? In this case, if I use the example number 1, this top case, if I use the first example, in this case, I'm basically saying, OK, I'm always going to be doing this checking. I actually don't want to use it, but I'm always going to be sort of doing it. The abstraction in this for loop that is being built. So, OK, without confusing extra, this for gets converted into the basic, it basically gets converted into this assembly code that says, OK, go check every element everywhere. Instead of doing this, I can build this abstraction where I'm not losing out in performance. So zero cost abstractions basically means that, if I'm not using something, I should not be paying for it. Right? I hope that makes sense, or I hope I didn't confuse people more. But anyway, we'll talk more about that towards the end if there are questions on that. Now, the other part is about all the standard types in Rust. That means you know about your primitives, which is your integers, your strings, your floats, etc. Now your user-defined types like structs. This is how you would normally define something in Rust. You basically say, okay, I need a struct. Let me call it circle. Then they have their members, or what you call fields. Then, sorry. And then there's this thing called a trait. Trait is nothing but, for people who've worked on Java, you may think of this as an interface. For people who worked on something like Swift, you may call this a protocol or something like that. Obviously, it's not the exact same thing, but it's very similar to it, where types implement traits. So implement hash area for circle, you're basically going to implement this method. So the moment you implement a trait for a type, the behavior is now acquired for that. That trait has been acquired by that type, right? So that's I will not go into too much into traits because there's a lot more. Then this other thing, this is pattern matching. By far the most, at least for me, the best thing about Rust is this particular thing, which is pattern matching. This match statement is like a switch statement. You can just say, okay, X is 3 over here. So let me say if X is 1, give me this. If X is 2, give me this. If X is 3, and if Y is not equal to you, give me this. You can sort of do this very, very intuitively in Rust using this match statement. So this is a blend between, usually you would see this somewhere in functional programming. Now that's actually available in Rust. Now the benefit, or the bigger part about this, or the best part about this is, there's also shadowing, which is you can, if I go ahead and say I want to print, if I say I print X here, I print X here, sorry, yeah. If I get this print statement, I get 8. If I hit this print statement, I get 12. If I hit this print statement, I get 8. Again, I get 42. X can be redefined in different scopes. So you can define a scope and you can shadow the same variable throughout the life of that life of the program. That's useful in some cases. It might be confusing in some cases, but it's useful. But getting back to pattern matching, this is one of the biggest benefits of Rust in my opinion, or one of the best design decisions. You can take something called an enum. An enum is exactly what it means in C as well. You have multiple variants of a type, and you could actually mix the match statement, which is this, with an enum. So for example, if I said I have a sum can be any one of these, which can be a simple foo that doesn't hold any data. It can be a bar which holds these two types, or it can be a baz which actually holds these two types. In this case, it's actually a struct, but anyway. So when I instantiate a foo, which is nothing but one variant, I just create a foo, and I say match foo. Technically, according to this implementation, it's going to pick this implementation, right? Now, and then you can start picking out values from baz directly, destructuring baz directly. So it's very, very richly typed enums, and it becomes very useful when you're actually doing your implementations. You can just think about it when you're thinking about, let's say, you want to create a TCP stream. You're probably going to get bytes, or you're probably going to get, 32-bit some integer, depending on, whatever implementation you have. It's very, very easy to sort of just say match on whatever type you got. If it's this, do this. If it's this, do this. If it's that, do that. Or if it's this, then pick the value that was exposed within that type. Pick the X value, pick the Y value. It becomes very easy to sort of write your code, and also very, very simple. Something like this to be written in C would have taken a lot more lines, and it would have looked a lot more messy. So that's a good thing about Rust. Then the other thing about mixing functional and imperative style is this concept of closures. When we talk about closures, its closures are simply higher order functions, or you can also call them nameless, anonymous functions. Anyway, so if we see, we have num, which is, say, we've just said assign 5 to num, and then we're saying plus num is not exactly an integer. It's an actual function. It's a closure that we've defined over here. It says takes a value, which is an i32, and returns that value plus num. That's the implementation that you see over here. And this idea of actually, functions are being treated as like normal types and objects is a first-class part of. So basically, closures are all first-class citizens of Rust. They're not like bolted on, etc. Now, this is where you feel like you're programming in a higher level language, not really. You're not programming in a lower level language like C, because this does not look like C. The capturing part that you see over here, I declared count outside of this scope. So the way a closure is usually defined is you have these two pipes, and then you have these curly brackets. This is the body. These are the input arguments. And whatever the last line is, that's the return type. Right? In this case, if it's a semicolon, that's not a return. Whatever's returned without a semicolon is the return value. So over here, what you see is that we are basically calling, this inc is nothing but a closure. So when we call it, we are actually capturing this variable 3 from the outside, and we're adding 1 to it. So when we call this one once, we get a 4. When we call it again, we actually get a 5. That's the capturing part, which is usually only available in a higher level language like Go or Java or something like that. That's now available in Rust, but you can also do systems programming in the same method. Right. Then this is a little more involved as an example. You can always write code like you write it in C, right? You can write this. This is a function that basically it's trying to find the sum of odd squares. You've given it a number, something like 1000. In this 1000, 0 to 1000, find the odd numbers, square them, give me the sum of it. That's the implementation. Pretty much in C, you would normally write something like this, right? In Rust, you can actually go do something like this. So this does not look like C at all. So each function you see over here is actually a closure that's passed to this. So basically you're saying, take all the integers, the range that you've taken, then square them up, which is n times n, then only take the 1000, the numbers below 1000, then check whether it's odd or not, those numbers, then sum all of them up. Right? Map, take while, filter, fold. This is the functional aspect of Rust. All right. Now coming to the key part about Rust. This is the key ingredient of Rust, at least the number one thing that is quoted whenever you talk about Rust is ownership and borrowing. How do we do memory management in Rust? We don't have a garbage collector. Great. So how do we do it then? And that too, how do we do it right at compile time? That means when the compiler is compiling, it checks your code to see if there's any ownership or borrowing issues. If there are none, it compiles. If there is one, it does not compile. The way it works in Rust is every value that you've declared or defined in your code has an owner. It's more like you can think of it, loosely speaking, you can think of it like a library. Not a library, is a person who owns a book. I'm the owner of a book. I hold that book. Great. I can probably lend it out to somebody, but they are not allowed to, sort of sell it or do whatever they want with it, right? I've lent it out. They just, are going to be holding on to it. They can use it and then give it back. All right. So that's the analogy over there. Every value has an owner. And until that owner, is alive, in the sense that when I say the owner in this case is x is equal to 5, the value 5 that's in memory is owned by x. That's what I mean. Until that owner is alive and it is not out of scope, it is not gone out of scope, till that point in time, that value exists, right? That's the key point. Now you can also take references to that value, which means we'll talk more about these references, but those references are, I can get a reference to it, which means it's like the book lending example. I've borrowed that book from the owner. So I'm borrowing that book for some time now. So that is something that called a reference over here. Just a very loose analogy, that is. The important thing is references are always guaranteed to be correct in Rust. You cannot just create a reference like in C. They are all statically tracked. They all have a lifetime. And that's the difference between references and pointers. Every reference is valid. In Rust, you have pointers, but they are not exactly safe to use, but you do have pointers for, when you want to use them. And that's what I mean by all references to all values are known statically. That is what I just explained is called RAII, resource acquisition is initialization. You cannot create a reference that points to nothing. You just cannot. It must refer to another owned object. That's the important thing about Rust. They're all guaranteed to be valid at compile time. That's the Rust reference guarantee. So the biggest thing about ownership of borrowing is very simple. It's saying that when there's a value that's in memory, there can be one owner and there can be with that one owner, there can be one borrower, one mutable borrower, or any number of immutable borrowers. I hope that makes sense. You can have any number of people borrowing that value immutably, which means they have read access to it. Or you can only have one borrower who has read-write access to it. Right? So the other point is when the borrower borrows something, the owner does not have access to it. Right? That's the key point about Rust. And the way that's applied, we'll see in the next slide. As I'm mentioning over here, either mutation or aliasing, not both at the same time. And that's enforced by the compiler. So there is no need for a runtime. It's memory safe. And you also get data race safety. We'll talk about data race safety in the next few slides. So by default, Rust variables are immutable. That means you can't go ahead and so when you actually say let x equals 5, you can't, in the next statement, you can't say let x equals to x plus 1. You can't do that. You would normally be able to do that in C, but you can't do that over here. You must ensure that you first declare that that variable is mutable. That means you can change its value during the lifetime of that variable. That's what this means. You can't do something like you declare A, that's just saying that, I have an A value, I've already assigned it 0. Then you're trying to change it. That's an error. Because you've already assigned it once, you're trying to reassign it. You can't do that. Or rather, trying to mutate the value of A again. So what you simply do is you add mute. So that's the mutability opt-in that you need to do in Rust. Then ownership. Ownership in this case is very simple. You're saying we have a vector. We've instantiated a vector. We call it V. Now we have transferred V to V2 by the second statement. Second statement is saying that V has been passed over to V2. When you try to access V again, you will get an error. You cannot access V again because ownership has been passed over. You no longer exist, in other words. V is no longer valid, in other words. The reason for that is If I created a scenario where v and v2 are just pointing to some vector, then again I have that double free use after fee problem, right? With Rust's ownership concept, you can only have one owner per value, right? So vector is one value. I can have one owner. So v says, okay, I'm going to transfer ownership. So v2 has ownership now. v0 does not make sense anymore, right? That's what we call use of a moved value. That's what this is saying. We've got v on the stack and vector 1, 2, 3 on the heap. So basically, v is a pointer to the vector on the stack, sorry, on the heap. And then now we've transferred over v2. Once we've done that, we're trying to access it again. It is not possible. OK, and then same thing, ownership can again be moved across functions as well. So if you see over here, we have a vector, which is do anything as a function. And what we're trying to do over here is we're trying to say that this is basically, again, as you see in the previous segment. Sorry, let me just go back. V is a vector. So V actually lives on the stack. Vector is allocated on the heap. You're passing V into do anything. When you pass V into do anything, you've given up ownership. You've transferred ownership. Main function no longer has access to V. But if you try to print it again, you're going to get an error, right? V in the do anything function, now you can do anything with it. And then at that, that's the point where it gets dropped. When do anything returns, V is gone. Because we've given it ownership, it did whatever it wanted with it, and it ended. It did not return it anyway, so it's done. So that's across functions. Now, you could obviously do it, the wrong way is what is said over here, but you can obviously do it a little differently. You can return the value, and you can expect that, okay, I've returned the same V is what you might think, but that's not actually true. What happens is this V1 and V2 are two vectors. I basically pass that to foo, which is over here, and that returns, V1 and V2 again, right? That's good. But this V1 and V2 and this V1 and V2 are not the same. They're actually different. Okay. That's how Rust keeps a track of all of these owners, the people who have the people who have references, mutable references, and the owners. The compiler is keeping a track of all those things when compiling your code. Right? Then the previous example, if you were to actually use the right way or a better way, if you're doing it, instead of passing ownership or transferring ownership completely, you can pass by reference. This is what we call an immutable borrow, which is just a reference. This is what we call a mutable borrow or a mutable reference. All right. So I have x equals 3 and y equals 5. I am going to borrow this immutably. Who is going to borrow this immutably? That's the function signature. Then y is going to borrow this mutably. That's the function signature, right? In this case, main is still the owner of these two, or rather x and y are still the owner of these values. I'm just lending this out to foo so that they can do what they want. They can read or read write, depending on whether they have mutable or immutable access. All right. So this is how Rust and ownership and borrowing works in Rust. OK, the same thing if you were to take it a little more advanced and talk about things like, OK, all of those were just very basic examples. If you wanted to talk about something a little more involved, take the example of a mutex. A mutex is something that allows synchronized access. That means you can have multiple threads that are executing concurrently on a system, and they may need access to the same piece of data. So you put that in a mutex, whichever thread gets a lock on that mutex, they get to work with that. So the way this can actually work in our case, if you apply the ownership and borrowing concept to this, you will see that when we look at this statement, which is we create a mutex which contains this hello string, we lock it, and we get the lock string. Then once we acquire the lock, we're okay to go ahead and modify, do whatever we want. That's the whole concept of a mutex. So when we do that, we don't have to actually manually call something like drop the lock. When it goes out of scope, this implementation is already there. It gets called. You can also customize it if you want, but that's a different story. But it's already there. You can drop the lock so that this mutex is now again available for locking. Right? And here's what happens again in the next case, where this is the string that is present inside the mutex. So at this particular location, you are going to be dropping everything, the mutex and the data that is contained in the mutex. So you call this implementation. All right. This may be a little confusing at first, but this is how ownership is working. Mutex is instantiated. You get an M. When you do an m.lock, what you get back is a mutex guard. That's a type. Just think of it as a type. What we're trying to say is that after this point, you don't have that mutex guard. It's gone. So you shouldn't be able to access it. And when we actually hit this point, this implementation is getting called and it's dropping the lock. Similarly, for the same case over here, because this is the end of scope and this is how long the mutex is going to live, we're going to drop the mutex and anything that's contained inside the mutex. Right? So that is what, by the way, drop is nothing but a trait. You might have seen the trait one before. That's why I didn't want to cover it extensively, because you can use it in such a fashion. OK. So what are the most important details about ownership and borrowing? The important thing is you cannot borrow a mutable reference from an immutable object, in the sense that if I declared something as immutable, I cannot take a mutable reference to it. It's immutable by default. So immutability is the default. You cannot borrow more than one mutable reference. As I said, let's say you declared something as mutable. Let mut x equals 5. Then you can only borrow it mutably. That means ampersand mut can be only performed once. So that you don't end up with a scenario saying that there are people who are reading it and there are people who have read-write access to it. That scenario you don't create. That's what we call atomicity. Then the other piece is that no simultaneous mutable and immutable references to the same value, which I just mentioned. You can't have mutable and immutable references to the same value. That simply, just that alone ensures that there are no race conditions. One thread is writing, the other thread is reading. That's undefined behavior. That does not happen because of the ownership and borrowing concept of Rust. And then the lifetime of a borrowed reference must end before the owner. It means I've first declared some type and then I borrowed it. Because I'm the borrower, after the owner has gone away, I can't still keep holding on to the borrowed reference. That is exactly what a dangling reference is, or a use after free is. That is also not possible with ownership and borrowing. All right, I'll just take a pause. Any questions to this part?
No, I think.
Right. So this is a comparison between, you do have mutability and immutability in Rust, sorry, in C++ as well. That means you have immutability and references, but it's actually the reverse in C++. In C++, you have this complicated system of, this is a non-const pointer, this is to a constant value, lots of stuff. In Rust, at the bottom, you see it's very simple. I can say, OK, I've declared something as mutable, x equals 5, and then I've reset it to 10. Then I'm saying that, let me just say there's some y, and I'm going to say that it is a mutable reference to x, or mute y is a mutable reference to y. These 4 pieces are exactly what's defined on top in C++. Now I leave it to you to sort of tell me which one is simpler. I think the bottom one is simpler. The other one, the top one, is a little more, you have to pay a little attention to what you're doing. Yeah, and then the last concept that I have is, we've talked about ownership and borrowing. The last piece that I have is what's called a lifetime. Lifetimes are concepts that we talked about references so much, so it makes sense to talk about lifetimes, because references have lifetimes. What do I mean by that? So let's look at some stuff on the left-hand side first. We have a main function. We declare a value, if we call it 5, and then there's the bad reference function that we're calling. The problem over here is we're just calling this function. It declares this, it defines this value called x equals 10, and then you're trying to return a reference to it. So can anybody tell me how long does this last? Just by what we've discussed so far. Any idea, just any number? So what I mean to say is, when I say how long does this last, does this live beyond the bad reference implementation or not?
I think it is, because we are throwing it from the function bad reference and catching it in the xref.
Right. So what's happening over here is x has a lifetime. Right after this bad reference is done, x is gone. X doesn't exist according to the Rust compiler, but we are returning a reference to x. So that's basically not valid. And that's why it doesn't work. In this particular scenario, if you try to print xref, you're going to get an error actually. If you actually wanted to do it in the right way, what you'd normally do is you'd say, okay, you see this this little tick s over here and here and here. It may look a little daunting, but it basically is what we call a type parameter. It's basically saying that this s can be any value that I come up with. I can say, lifetime, or I can say lf, whatever. It's up to me. I'm just calling this s. What's happening over here is I instantiate a string. I basically say that I allocate this string called my name is Kevin on the heap, and then I get my y value. I'm just passing that I'm passing it as a reference to good reference, right? When I pass it, all I'm doing is I take whatever I get and I look at the 3rd to the 7th element, which is basically the name. I'm looking for this particular, slice, and I'm trying to sort of say, okay, let name equals this, and I'm going to return this name. Now the key point over here is the owner of this slice of data is actually sitting here. So he's alive. He's not gone anywhere. So I've passed it in, and I've ensured that, please ensure that the lifetimes match up. That means whatever I gave you as a string, it is supposed to live for s. Then the return value can also only live for s, not more than that. I'm clearly calling this out in my example here. So yref has the type this, which is along with the lifetime, in which s is the name of the name given to the lifetime of y. So references, at this point you can think of references as lifetimes, in the sense that, as references having lifetimes as pointers, pointers being around for a certain period of time. So this y is the actual owner, and this string is actually a part of sort of y. If y goes away, and if I try to access this, then that would be an error. But this is not an error in this case, because I'm passing y in and I'm only looking at the first few pieces, and I'm again returning whatever name I got back. right? If that makes sense. So that's basically the concept of lifetimes. Lifetimes basically say that every single reference, mutable or immutable, can live as long as the owned data is around. And you have to make sure that that happens. And you can do that by simply using something like this in the types. Right? So the contrast was what you saw in the previous slide. If you try and do something like that in C, we'd end up with dangling pointers, because you see over here in this particular C code, what does NP really point to after the function returns? What happens is if NP is dereferenced after being returned? That's a question that, we have no answer for because it's undefined. It's a dangling pointer. Right? So because the local variable is allocated on the stack, a temporary function, local storage area, which is you're getting a pointer to that, you're basically creating a pointer. And then you're saying reference is returned, but the variable is now out of scope. The actual owner who's supposed to have owned that is no longer available, but I have a reference. Right? So that's sort of the problem. And where does this really help? When you do something like concurrency. That means when you have multiple threads that are running concurrently, and you want to ensure that one thread doesn't end up reading and the other one reading, and one is reading and the other one is writing to the same location at the same time. That cannot happen because of what you just saw. So in this example, this is a normal data structure. This is a function foo. We are allocating this data structure on the heap. Box new is basically box on the heap. We get the result, whatever. And then to create new threads, we say that foo is one executing thread. Thread spawn is going to create a new thread, and then it's going to pass transfer, or rather take mutable borrow to the result, which is res over here. And then it's going to increment whatever is inside it, the A field by 1. It's going to do that. Now, when this actually happens, you get an error when you try to compile this. Because here, when the foo is actually executing, this is already mutably borrowed. This thread is running. It's mutably borrowed, it's running. And you're again asking me to, at the same time, you're probably asking me to increment the value again of A. So the other thread may be reading or writing at that time. I don't know what to do. I might end up creating undefined behavior. So that is how we prevent a data race in using just the simple concept of ownership and borrowing. Right? So that's about it. I guess we are bang on time, but that was a lot of slides to go through. So I'll just wrap up by saying that Rust defies convention in the sense that if you use C or C++, you have more control, but you have very little safety. And if you need more safety, you lose control. That's on the right spectrum. Haskell, Python, Java, C#, all of that stuff. Rust sits in between. You have the control of C, but you also get the safety of a managed programming language. Right? So that's pretty much what I had for today. I know we have very few minutes for question and answer, but if there are any questions, I think I can sort of take them. And I'll just no other questions, then I guess we can stop the recording and close this session. But before we go, thank you everyone. And in case there are questions, thoughts, ideas about Rust, how you'd like to get involved, where can we find more information?